Hello, I'm presenting MoE-GRPO, Optimizing Mixture of Experts via Reinforcement Learning in VisionLanguage Models, joint work between Korea University and KAIST, accepted to CVPR 2026. A mixture of experts reduces the cost of large vision language models by activating only a few experts per token. At each layer, a gating network scores all experts, and standard MoE deterministically selects the top K, always the highest scoring ones. This greedy rule is simple and efficient, but it never explores alternative expert combinations. Potentially better routings are never even tried, and the model overfits to a small subset of experts. Our key idea is to treat expert selection as a sequential decision-making problem and optimize the routing policy with reinforcement learning. Let's compare the two behaviors. On the left, deterministic top K, token after token. The router picks exactly the same highest scoring experts. 6 of the 8 experts are almost never selected. On the right, MoE-GRPO. During training, we sample multiple expert routings. These are our rollouts. Each rollout generates an answer and receives a verifiable reward. Rollouts that chose good expert combinations get positive group relative advantages, and the gating network shifts probability toward them. Early on, the policy explores widely. As rewards accumulate, it exploits the combinations that actually work. The router learns a policy instead of following a fixed rule. Here is the overall pipeline. Given an image or video with a question, the rollout module samples G-expert routing policies, each a full sequence of expert selections across layers and tokens. The model generates an answer under each routing. A reward function scores it, and advantages are computed relative to the group. Training combines two objectives: token GRPO, the standard token level objective under each sampled routing, and gate GRPO, which applies the same clipped surrogate directly to the gating networks, turning one binary reward into dense supervision at every layer and token position. Since the gates are trained from scratch, there is no reference model and no KL term. Unrestricted exploration over sequential expert choices is slow and unstable. Our modality-aware router guidance fixes this. We measure how often each expert serves vision versus text tokens, deactivate the bottom 25% for each modality, and sample the K experts from the remainder. Exploration stays on modality-consistent experts while keeping enough diversity. At inference, selection is plain deterministic top K, zero extra cost. For evaluation, we convert intern VL 3.5 1B into a mixture of experts with 8 experts, 2 active per token, and fine-tune on 100,000 visual instruction examples. Across 9 image and video benchmarks, MoE-GRPO reaches 56.0 average accuracy, 2 points over deterministic fine-tuning, and clearly ahead of both stochastic variants. Notice that injecting randomness alone does not consistently help. What matters is explicitly optimizing the routing policy. The learned routing also generalizes. On ClipMoE, cross-dataset transfer improves by 3.1 points over deterministic fine-tuning, winning on 9 of 10 datasets, where deterministic fine-tuning actually degrades the base model. On out-of-domain ImageNet variants, MoE-GRPO gains 1.5 points. Diverse expert use makes the model more robust. Both objectives are necessary. Token GRPO alone reaches 53.9, gate GRPO alone 50.9, and combining them 55.7. Modality-aware guidance beats modality-agnostic exploration by up to 1.5 points, and the training curves show why: faster reward growth and lower variance within each rollout group. So what routing policy is actually learned? Under deterministic fine-tuning, just 2 experts receive over 90% of all traffic. MoE-GRPO spreads activation across experts, raising routing entropy from 1.05 to 1.82. At the task level, the effect is the opposite. Expert distributions become more distinct per task, with Jensen-Shannon divergence rising from 0.06 to 0.20. Balanced at the token level, specialized at the task level, and it shows in practice. Here, the baseline miscounts the dogs, while MoE-GRPO answers correctly. To summarize, MoE-GRPO learns expert routing with reinforcement learning, exploring beyond deterministic top K under modality-aware guidance, with consistent gains and better generalization. The paper and code are available here. Thank you.